All right, today we're going to be doing 5.4a, which is fundamental theorem of calculus. So, very fitting for the class we're in. So, you already basically know how to do the fundamental theorem of calculus. You just never knew it was the fundamental theorem of calculus. It essentially branches or combines the two branches of math, differentials, and integrals. Sadly, we won't really get to the branching that much in this class because we're running out of time. But you should at least know that the fundamental theorem of calculus states that if you're evaluating a definite integral, you can do so by plugging the upper boundary into the antiderivative and subtracting it from the lower boundary plugged in, which you all know how to do because that was the whole first thing you did on your quiz. So what I want to focus on today is the theoretical aspect, understanding the graphs, all that, and harder integral calculations. Within still stuff that you know how to do, but more advanced algebra stuff. So, of course, you guys know no plus c is necessary when calculating definite integrals. You guys know that. All right. First one. We want to take the definite integral of 3 from 2 to 7. So step 1 is to take the antiderivative. What would be the antiderivative of 3? 3x. We're going to evaluate 3x from 7 to 2. So that's going to be 3 times 2 minus 3 times, 3 times 7 minus 3 times 2, which is 21 minus 6, which is 15. So that one was pretty easy and straightforward. Now, I will mention, you don't have to do this, but how this compares to the graphing. This is a function that goes through the value y equals 3, so it's like here. And then we would be looking at it from 2 to 7. So this is a rectangle, right? The area of a rectangle, if you were to graph it. Remember when we learned about graphing? Okay. Letter B. Now you might be like, what is that?
Yes.
But do you guys remember that yellow sheet where I gave you all the sine and cosine derivatives and you had a little quiz to memorize them all?
Yeah.
But you probably just dumped them from your brain at this point.
Yeah.
So if I give you a question where I want you to do anything but sine, cosine, or tangent, I will either let you know in advance on the test or quiz to know what one to know, or I will give it to you, a table. But I will give it to you in this form. I'm going to say the derivative of cotan is negative cosecant squared. Is that sufficient information to find the antiderivative of negative cosecant squared? Yeah, because it's just, what is it? Cotangent. You just have to know to go backwards. Okay, I'm not going to tell you that, but you have to know that. So, this is going to be, what would be the antiderivative of 2? It would be 2x, but we're not using x, we're using 2 theta. Now, notice it's negative cosecant squared, so how does that affect things? It becomes positive cotan. And we're evaluating that from pi over 2 to pi over 4. Now you guys can go ahead and start plugging in. I'm going to put a graph of this thing up because I want to talk about it for a second. Because this is kind of a cool thing that you can see. How many of you guys remember what the graph of cosecant looks like?
Is it like
It's kind of a weird graph. Okay. So we're going to plug them in. So we have 2 times pi over 2 plus cotan, not cosecant, of pi over 2 minus 2 times pi over 4 plus cotan of pi over 4. Now we're going to talk about it. Now, of course, this just becomes pi, right? Everybody good with how I just got plain pi? Now, cotan is actually 1 over what? It's the reciprocal of tangent. It's the reciprocal of tangent. So I don't know how much you guys remember about reciprocal functions, okay? But reciprocal functions look like this, all right? I'm going to plug in tan so you guys can see it. Okay. So this is the graph of cosecant squared, okay? Now, what you're going to notice about this graph, maybe, Yes. Oh, we're not looking at cosecant though. We're looking at tan. Cotan. That would be why the graph doesn't look the way I wanted it to. I was like, what's happening? So we have our graph of cotan squared. Is this graph defined everywhere on this interval?
No, I can't see it. No.
Just think about it for a second. What are these? What do we call these that are in between here?
Vertical asymptotes.
Yeah, they're essentially vertical asymptotes. So this graph has a lot of gapping in it, okay? Would it be difficult if I asked you to find the area, say, from 0 to 5? You would find the area here, but what's going to happen when we get to this section? It's going to get really cloudy and difficult to figure out because where do you find the area when there's an asymptote? That's really complex, right? Now, there is math that assesses that. But what you're going to notice is, see how the graph looks. Not easy to find the area of this thing over a defined integral because of those asymptotes, those discontinuities, correct? What I want you to do now, isn't pi over 2 the same thing as what? What degree measure? 90? So I want you to do 1 divided by tan of 90 in your calculator, or pi over 2, whatever format you are in your calculator. 1 divided by tan of 90 or pi over 2. And you get an error, okay? That means that tan of 90 is 0, so 1 over 0 is undefined, because that is where a vertical asymptote exists on the graph. So we're trying to find an area where there's a vertical asymptote. We cannot do that. So this is actually an undefined integral. Because you can't find an area of something that has a big gaping hole in it, right? It's something like this, okay? And they want you to find the area here, and that's not possible because the function doesn't exist there to find the area of. What's up? Yeah, it's fine. It's been broken. People just keep dropping them. We still got to keep it though for count. So.
Yeah, it turned on.
Yeah, but I have to be able to tell, like, I have to save them, or otherwise then it's like one other thing.
They stole it.
Who did?
No,
Oh, yeah.
stole it or something.
Alright, next one. So this one here, everybody should be pretty confident with, I hope. This is x cubed plus 5 halves x squared plus what? Or minus? Yep. Everybody good with how I got that one? Now we're just plugging these guys in. So we get 3 cubed plus 5 halves 3 squared minus 4 times 3 minus 1 cubed plus 5 over 2 1 squared minus 4 times 1. This gives me 27 plus 22.5. Yeah, because that's 9 times 5 is 45. Half of 45 is 22.5 minus 12. This is 1 plus 2.5 minus 4, which gives me
Negative.
38, I think,
I got it.
for the whole thing.
Oh, okay, yeah.
So yeah, I just don't want to spend a ton of time on calculations, but you guys understand that one pretty well, hopefully. Okay. Now this is where things can get a little bit gross, okay? With this problem, okay, I want to just preface this. I want to go ahead and do the integral because the concepts in this integral are important to understand with the fractions. But when you go to plug these n values in, it gets so messy. We're just not going to actually evaluate the integral, but I do want to just at least take the antiderivative of it so you get practice with that, okay? So it's more of the conceptual understanding that I want you to see. Isn't this the same thing as 1/2 times this? Would you agree with that? That means I can take the 1/2 out front of my integral. Remember we learned about that in 5.3? Vaguely, maybe? Bless you. Now, this is just each of these individual terms divided by x to the 1/3, right? So I can rewrite it as x over x to the 1/3 minus 2 x squared over x to the 1/3. You see what I did there? Okay. What is the exponent on a plane x?
1.
1. How do we deal with when we have the same base, different powers division? What do we do? What is like x to the third divided by x squared? What would you do? You subtract. 1 minus 1/3 is what? 2/3. 2 minus 1/3 is 5/3, right? Do you all agree with that?
Mm-hmm.
Okay. Because that's like 3 over 3 and then 6/3. Now from here, we're going to take the antiderivative. So if we add 1 to 2/3, what is 1 plus 5/3? So this is x to the 5/3, but then if you divide by 5/3, it's the same thing as 3/5. Over here, this, we add 1 to 5/3, that becomes 8/3. When we divide by 8/3, we get 3/8. Now here's where the squirrely part comes in. When you try to plug these numbers in, I mean, it took us the rest of this paper, so I don't want you to check out just yet in the notes, so we're just not going to do the evaluation, okay? But what you could do on this one is you could evaluate it in the calculator to see approximately what it is. So if I gave you a question like this on the test, it wouldn't be this difficult, but I want to practice it because I want you to get familiar with fractions like this and be able to do with fractions, so that's why we should practice that, okay? But the plugging in, that's too much. We're not going to have one that difficult, I promise. What?
4/3 period.
Yeah, I mean, they just sat there and watched me, so I don't feel too bad. It was more poor me.
Yeah, if you started doing that, I would just tap out.
That's what I'm saying. I don't want anybody to just like tap out for the rest of the notes, because it's just, you all know how to plug numbers in.
Yeah.
It's just gross. Okay, that's the bottom line. So the next one says to find the area bounded by the graph. So this is the type of problem where it doesn't mention anything about calculus in the problem. Doesn't say anything about the integral, doesn't say anything about derivative. This is where you have to know what to do using calculus. So what do you think we're going to do?
Set it up.
Set an integral up. From what to what?
From 2 to 1.
Good. Of
1/x².
1 over x squared, which is the same as x to the negative, not 1/2.
-2.
That's a root. Yeah. Everybody good with that?
Yes.
Cool. Now we're going to take the antiderivative. When we take the antiderivative, we always do what with the exponent?
Add 1.
What's negative 1? What happens when you divide by a -1? It's the same thing as making it negative. Yeah. Now this is actually this, isn't it? Do you guys see why?
Yes.
Okay. Now we're going to plug in the endpoints. That's -1/2 plus 1, which is 3/2. Everybody good with that? Okay. This is the kind of question I would definitely ask you. I don't think that's too bad. Okay. Next one. Once again, no calculus mentioned. You have to understand what the question is asking you to do. Sometimes that's the hardest part about math, is being like, what are they asking, right? So they want us to find the area of the region bounded by the graphs. That's where calculus comes in, right? What is my integral going to go from?
0 to 5.
Good. Of x plus sine of x dx. What is the antiderivative of x?
X squared.
1/2 x squared. And then what is the antiderivative of sine?
Cosine.
Not cosine, negative cosine. Then we got to plug in pi and 0. Yeah, tricky. But it's okay. We're all smart here, we can figure it out. This is going to become 0, inevitably.
Zeros.
This becomes, yes, when they go to 0, that's always
So
nice.
happy when
Just get to throw them away.
Yeah.
Anybody know what cosine of pi is? Cosine of 180?
0, 1, -1.
-1.
Sorry.
You're about to get
We're
it.
just gonna go through them all.
Sorry, yeah.
Anybody know what cosine of 0 is?
1.
Uno.
It was either gonna be 1, -1, or 0.
Just keep guessing until you get it. So we got 1 minus 1. So it's just pi squared over 2, right? Make sense?
See?
Okay. If you don't know, the good news is if you still don't know your trig by now, you have a calculator. So I do get concerned sometimes, though, about your guys' trig. I'm not going to lie. Okay. Next one. So this is one of those fundamental theorem calculus problems that pulls in all of your knowledge of derivatives, graphs. You remember all this stuff where we used to look at the graph and be like, oh, it's inflection point and all that stuff? We're going to talk about that a little bit. So, yes. So,
Because I remember not liking uniform. Yes, I just remember that.
so the graph of a continuous function f with domain from 0 to 8 is shown below. Let h be the function defined by h of t equals the integral from 1 to x of f of t dt. So this is one of those problems that looks really confusing when you first see it, okay? But it's actually not that bad. So all it's saying is when you take the antiderivative of f of t, it becomes h of x, right? So therefore, if h of x is the integral of f of t, then f of t must be the integral is antiderivative, right? You're close. The derivative. If you have to integrate something to make it the function, that means that the thing you were integrating was the derivative. You guys got that through your heads? Okay. I know it's a lot to process. Sure. If you have to take the integral of some function to make it become another function, that means that it was the function's derivative to begin with, because it's undoing that differentiation, essentially.
Okay.
Which is something you guys probably already know, but you haven't seen it phrased that way. All right, so it wants us to find h of 1. Now the issue is this is not the graph of h, this is the graph of f. So what we can do is we can use this right here. If it tells me h of 1, what do you think I should do with all the x's? Turn them into a 1. It would be 0, right? Because the integral of anything to itself is always 0. So what I did here to recap, in case anybody missed it, see how they told me h of 1, so I plugged in 1 for x, and then I see that the integral of anything from itself to itself is always 0, so I didn't even have to know what f of t is. Got it? Okay. Next one. Is h of 0 positive or negative? Well, let's see what h of 0 even looks like, so I can visualize what's happening. So it's the integral from 1 to 0 of f of t. Now what you should notice right off the bat, what's weird about this integral? It's flipped. Therefore, whatever it looks like over here, it's going to be the opposite, right? So if I look from 0 to 1, this area, does that area appear to be a positive area?
Yes.
Yeah, we don't care what the area is, but it is a positive area. How do I know it's a positive area? Therefore, if I go the opposite way, it's going to become negative. So that's like a critical thinking question, right? So you have to look at the graph, see what it is. If it's flipped, it's going to be the opposite. All right.
Well, even if I said like this on the test or anything like that, would you have to actually find a value or have to write it out negative?
So it really depends on how much information I give you. If I don't give you enough information to you don't have enough information to find out what it is, you just know that it has to be negative.
Yes.
So you'll see both types of questions on there, but just accordingly how much information I give you. The value for x in which h of x is a maximum. So remember, we're looking at the graph of the derivative of h of x. So we know that maximums occur when the derivative goes from a positive to a negative. Do you guys remember making these little tables? Up, to down, when the derivative does that, it's a maximum.
Oh no.
So, do you see how here the derivative is positive, but then at 4, after 4, it changes to a negative. So at x equals 4, the derivative goes from positive to negative, which means that if the derivative goes from positive to negative, the function must have a maximum at that point.
Yes.
Make sense? Next one is minimum. For minimum, the derivative goes from negative to positive. But if we look at our graph, is there ever a time when the function goes from negative to positive? No. So therefore, there is no minimum. And then lastly, find the x-coordinates of all the points of inflection. Do you guys remember what a point of inflection looks like on a derivative graph? Don't overthink it.
Isn't it where it flips? Like,
Yeah,
like that?
sort of. Not where it has, because that would be a point of inflection on the function, but this is the derivative. When the derivative is 0, that's where the function changes direction, right?
Well,
So-
I'm saying like when it like curves.
I know what you're saying, but it's not, that would be on the regular function. So for the derivative, it's where the derivative is what? 0. Point of inflections occur when the derivative is 0. On a regular function, yes, it would be where the function has flips. So it would be at x equals 1, x equals 4, and x equals 8. So remember, when we're looking at derivative graphs and regular graphs, they have different rules about them, different things that make things be something else, right?
So we're looking at a derivative graph here.
Correct.
Gotcha. Okay.
Which means that we have to analyze it differently than if we